Recording and audio. And what is the date? 3rd. So, Gesundheit. We're going to pick up today on chapter 3.5. That's what we were talking about last time. You gonna make it? Projectile motion. Specifically, we're looking now at motion in 2 dimensions. Galileo went to some effort to demonstrate that you could treat motion in 2 dimensions as 2 separate independent events. That you could treat the motion of an object in the horizontal independently of the motion that it undergoes in the vertical. And if you look on page 58 and 59, you'll see a sketch of projectile motion in figure 318 and a photograph of basically the same thing in figure 319. The photograph in 319 is a strobe photograph where it photographs the 2 balls as they fall, with the red ball just being released from rest vertically, the yellow ball being released from the same height but with a horizontal component to its motion. And if you will look at the photograph, you will notice that at each moment in time, where each little ball, each ball in the vertical there represents a separate strobe of light flashing, and you will notice that each ball falls the same distance in the same time, in both cases, independently of any horizontal motion or any horizontal translation it undergoes. This is something we kind of take for granted nowadays. When Galileo worked this out, it was not at all a given. It was not, it was not just accepted as a given that this was true. He had to go through some effort to demonstrate it. What we are going to do is we're going to test it. In fact, this is your lab this week. It's called projectile motion. And that's what you're going to do, is you're going to make predictions about how far a steel ball will travel once you release it from a spring-loaded launcher, which means this week everybody's going to have to wear safety glasses because we're going to be firing little steel balls across the room, hopefully not very far. And so far, nobody has been injured in one of my classes. Let's keep it that way, okay? There's a couple of these experiments that I get nervous about. This is one of them. Centripetal acceleration is another one. You'll see why when we get there. How many of you still have your kinematic equations written down? Let's see. Let me find them again. They had, there they were. There they went. We have velocity in x is equal to the initial velocity in x plus the acceleration in x times time. Tyler, good morning. Make sure you get signed in, and I've got stuff to hand back to you before you leave. We have x, which is equal to x sub naught plus v sub naught in x times t plus 1/2 acceleration in x times t squared. We also derived velocity in x squared is equal to v sub naught in x squared plus 2 times a in acceleration in x times x minus x sub naught. And finally, the average velocity in x is simply the average of the initial and final velocities. Of course, all of these are based on the assumption that acceleration is constant. It could be 0, it could be positive, it could be negative, but it's constant. We also looked at some vertical, when that constant acceleration was just g, the acceleration due to gravity. And we just basically rotated these equations to 90 degrees so that v sub y was equal to v sub naught in y minus g times t, where g is 9.80 meters per second squared. Y sub naught plus v sub naught in y times t minus 1/2 g t squared, v sub y squared, v sub naught in y squared, minus 2 times g times y minus y sub naught, and the average velocity in y is the average of the initial velocity and the final velocity. The same exact equations, except A is negative because it points down and it's a specific number, g, the acceleration due to gravity. We used these equations to solve motion, find out how far something would fall, how long it would take, how far it would travel, how long it would take. And we solved these, but we did them independently. When we talked about a rocket going vertically, that's all we talked about. We assumed it went straight up, and then it came back straight down. When it was moving horizontally, We assumed it was in a straight line. It might go forward and then come backwards. A runner might race across the finish line and then end up coming back across the finish line, but it would all be horizontal. How many of you have ever watched this, a NASA launch? Ever watched the space shuttle launch? Only one of you? Seriously, show of hands. How many of you watched the space shuttle launch? Yeah. Has it ever just gone straight up? No. It goes up and then it starts to lean over and veer off in one direction. And it generally rolls over on itself. And we're not going to get into rotational motion. But in real life, motion is not restricted to one dimension. It's convenient to learn how to deal with these equations and how to calculate and analyze motion in one dimension because it simplifies the thinking and it helps us to wrap our mind around it. But in reality, when an object is moving, when it's undergoing translational motion, it's happening in at least 2 dimensions and usually in 3 dimensions. Well, just like it was easier to get our minds wrapped around how to do this mathematically by dealing with just 1 dimension, now we're going to take the next incremental step and we're going to analyze motion in 2 dimensions where the ball is not only traveling up and back down, but it's traveling horizontally at the same time. The batter hits the baseball at a certain angle with a certain velocity. Will that baseball will it be a home run or an infield, what's the word? Infield double or a ground rule double? Or, I don't know. Where will the ball hit? Will it clear the fence or not? Car drives off a cliff. Thelma and Louise, they drive off the rim of the Grand Canyon. How far into the Grand Canyon will they travel before they hit the ground? How long will it take them? What Galileo was kind enough to demonstrate for us and what we're now going to accept and later this week in lab test empirically is that we can treat both axes of motion independently. So let's start by looking at problem-solving technique that they recommend here in the book. It's on page 60. Solving projectile motion problems. By the way, if you can take your initial 4 kinematic equations and in your mind change them to the 2-dimensional versions, that's great. Frankly, all you have to do is change the subscript from X to Y and change A to G and make it negative. If you're not sure that you can get it right doing that, then you might want to go ahead and make notes of these equations and have them all on your card. They are going to come back and you will be using them. So, what do they recommend for the process for solving a problem in 2 dimensions? 1, as always, read carefully, choose the object or objects that you're going to analyze. That should be a given for any time you're solving a problem. You want to read the thing carefully and make sure that you answer the question that's being asked. It may show that you've learned something if you show how far something will travel before it hits the ground. But if the question was how long will it take before that happens, you need to make sure that that's the information that you solve for. Again, draw a careful diagram, just like we did when we were doing one-dimensional analysis. You'll be amazed how often it will help you if you will just take a moment, go ahead and waste some of that paper space and make a sketch of exactly what is happening, how is the motion going to transpire, what are you solving for, what's involved in it. Choose an origin and an XY coordinate system. As a general rule, and it isn't always the case, but as a rule, you're going to be best off if you choose x equals 0 and y equals 0, the origin of your coordinates, as the initial starting point. And you will be best served if you choose time t equals 0 as the moment that it all begins. But look at what you're solving for and make some educated decisions and choices about what will be the best description as far as enabling you to analyze the problem. Decide on a time interval. Now, this is actually important, because when we are doing these problems, we're analyzing the translational motion of the object or objects. We are not analyzing the forces involved in setting them in motion. We're not analyzing the forces involved upon impact. We don't care what the fuel efficiency of the car was as it was leaving the cliff. We don't care how hard the tires were spinning, or if they were slipping in the dirt or in the mud or what. We are only interested in the moment from the moment when the car first leaves the cliff, from the moment that the ball leaves the bat or the head of the golf club, to the moment that it hits the ground or the cup or the fence or whatever it ends up hitting. We don't care what happened before that. We don't care what happens after that. It's the motion in between those 2 points that we're analyzing. Number 5, examine the horizontal and vertical motions separately. And that's sort of the whole point here. Is that we can analyze the two of them separately. We don't have to try and analyze them concurrently. Now, sometimes you will discover, for example, the car leaving the edge of the cliff. You want to know how long it takes it to hit the ground. Well, that's simply a vertical. The only thing that's going to affect that is how fast it falls. So you're going to do a vertical analysis. If you want to know how far it's going to travel before it hits the ground, now that becomes a horizontal issue, but you're going to need to know the total time that it moves horizontally, which means you're going to have to solve the vertical issue first. Find out how long will it fly before it hits the ground. Then you can determine how far it will travel in that time. As before, list the known and unknown quantities, list all of the information you're given, and list what you don't know, what you need, what you're trying to find out, what you're trying to solve for. You need to do that in order to choose which equations are going to be most beneficial to you, which one's going to help you. And then think a minute before jumping into the equations. A little planning goes a long way. Apply the relevant equations Combining equations if necessary. You may need to combine components of a vector to get magnitude and direction. You may need to separate components of a vector to get vertical and horizontal initial velocities. I think the best thing to do at this point is to jump into one of these problems and work it. Let's work it through. Example 3.5 right here, driving off a cliff. A movie stunt driver on a motorcycle speeds horizontally off a 50.0 meter high cliff. How fast must the motorcycle leave the cliff top to land on level ground below 90.0 meters from the base of the cliff where the cameras are? Ignore air resistance. Okay, well, let's start by drawing a sketch. We have a cliff and a motorcycle. We know the height of this cliff. If this is y equals 0, then this is y equals 50.0 meters. We know how far this motorcycle needs to travel. If this is x equals 0, it needs to travel here to x equals 90.0 meters. What is the question that we're trying to answer? We know this is the motion that we want to solve for. The motorcycle leaving here and landing here, 90 meters away and 50 meters down. What is the problem asking us to solve for? V naught. Now, there's one other point here that I want to bring out for you. I want to make sure that you notice this. It says a movie stunt driver on a motorcycle speeds horizontally off of a 50 meter high cliff. That tells you what? That tells you that V sub naught is equal to some V sub x sub naught, some initial horizontal velocity, times I. Remember our unit vectors? And that it has no vertical initial velocity. So the initial velocity vector is all horizontal and nothing vertical. Now, choose I hope I didn't jump too far ahead and make a choice they didn't. Choose a coordinate system. Y is positive, and x direction horizontal with x equals 0, point where the motorcycle leaves the cliff. Okay, done all that. Choose a time interval. This is t naught equals 0 seconds. Which of our equations are we going to use? Well, what's the first thing we're going to need to solve for? once this motorcycle leaves this cliff, the time it takes that motorcycle to reach the ground is a given. It's fixed. So the first thing we need to find out is how long is it going to take the motorcycle to get from there to here? How much time does it have to travel this 90 meters? What we're asking is, we're wanting to know, is this initial velocity, v sub naught? Well, we know that 90 meters is equal to its initial x velocity times the time it takes it to travel. That distance. Until we know that how far it's got to go, we need to know how long it's going to travel in order to find out how fast it has to be going in order to cover that distance in that amount of time. Okay. Once we know the time, then we can simply write 90 meters divided by t, that many seconds will give us our horizontal component velocity in meters per second. So the first thing we have to find out is time. How much time do we have involved here? So that means there's only one equation up there that will give us time. Am I wrong? We don't need to calculate how far it's going to fall. We know that. It's going to fall 50 meters. We don't really care what its final velocity is. All we want to know is how long is it going to take. So let's use this second equation. Y equals y sub naught plus v sub naught y times time minus 1/2 g times time squared. Did I get that right? Okay. What is y? What is y? Final. Nope, the final y. 0. Y sub naught is plus 50 meters. What's its initial y velocity? Initial y velocity is 0. G is minus 9.80 meters per second squared times time squared. So, if we add 1/2 9.8 times time squared to both sides, we end up with, and I'll just do some rearranging here, 50.0 meters is equal to 9.80 divided by 2 meters per second squared times time squared. Pretty straightforward to solve this one. We just multiply both sides by 2, divide by 9.8, and we end up with 100 meters divided by 9.80 meters per second squared is equal to time squared. What's that? Somebody with a calculator. Say again. Somebody make up my mind. 10.20. Meters divided by meters per second squared gives us what? Seconds squared. They come back up to the top. So T then is the square root of 10.20 seconds. What's the square root of 10.2? Say again? 3.2? 3.20? 3.19? We started out with 3 significant digits. We've got 3 significant digits in all of our givens, so let's keep 3 significant digits. 3.19 seconds. That is how long it's going to take this motorcycle to fall 50 meters. That also now tells us how long it's going to be in the air, so we can now find out what its horizontal velocity has to be in order for it to travel 90 meters. We take 90.0 meters divided by 3.19 seconds, gives us, say again, 28.2 meters per second is our initial velocity in the horizontal, along in the x direction. So our initial velocity is, in rectangular form, 28.2 meters per second I plus 0 j. Now, just to see how many of you have been paying attention, without using your calculator, what would that look like if we converted it into polar coordinates? Just in your head, can you convert this rectangular vector into polar coordinates, or into polar form? What would it be? 28.2 at 0 degrees, exactly. Everybody see why that's true? Anybody not see why that's true? If you draw that vector, you get magnitude of 28.2 meters per second horizontally along I. And that's it, nothing else. So in polar coordinates, that's 28.2. It's the total magnitude. And its direction is at 0 degrees, perfectly horizontal. If it were completely vertical, if it was 0I plus some magnitude in j, then the polar form would be that magnitude at how many degrees? 90 degrees. You only have to break out the calculator when you have both are non-zero. Then you have to start using Pythagorean's theorem and the trigonometry to get the angle. Any questions about this one? Megan, welcome. Where's the sign-in sheet? Right behind you. Has anyone not signed in? Okay. And before you leave, I've got stuff to hand back to you. Does anybody have any questions about how we solve this in 2 dimensions? I'm not sure whether to be encouraged or not. It is straightforward. It is exactly what we have already been doing. Well, then let me ask you this. Does anyone have any questions from the homework assignment? Ah, there go the hands. Speak up. Say again. Number 10. And what? Number 6. Number 5. If we get to it. Let's see how many of these we can do. Okay, y'all are just being mean now. Let's make the professor perform, huh? Okay. Somebody read the first one to me. Number 10. What page am I on? Say again. 58. Are these the problems that are due this today? Then how did we fall behind? So these are week 5. Week 5 assignment. All right. Good enough. Number 8. No, number 10. A and B as shown in figure 335. Oh, right there. Okay. Let me finish erasing. Everybody got all these kinematic equations written down that they need? We took pictures of them. Everybody's good? Megan? Okay. We have A, $44.0 somethings at an angle of 28 degrees, 28.0 degrees. We have B, is 26.5 somethings at an angle of, what angle would that be at? Say again? Is that 180 minus 56? Somebody confirm that. 124 degrees, 180 degrees minus 56 degrees. And we've got C, 31.0 somethings at what angle? Francisco. What angle is C at? .270. Very good. Okay, those are our 3 vectors. A, the sum of the 3 vectors. Give the resultant in terms of A, components, and B, magnitude and angle with the x-axis. So we got to add them together. What does that mean we have to do? First thing we got to do is convert them all into rectangular form. What is C in rectangular form? Without your calculator, just look at it. It's 0i minus 31.0j. Exactly. Okay, what is A? Let's do the conversion over here. It's 44 at 28, right? So in rectangular form, it is equal to 44.0 times the cosine of 28 degrees I plus 44 times the sine of 28 degrees J. And somebody with a calculator, give me the numbers. Say that again. 38.8 I, 20.7 J. Somebody confirm these. That's what, okay. Then let's write that here. 38.8 I plus 20.7 J. Now we need B. 26.5 at 124. .5 times the cosine of 124 degrees I plus 26.5 times the sine of 124 degrees J. And somebody with a calculator? Did somebody get anything different than I did? Does everyone understand? Can everyone get this out of your calculator? Make sure that you're in degree mode. Somebody knows who I'm talking to if you've looked at your homework I've handed back. All right, well, let's write this over here. Minus 14.8 I plus 22.0 J. Okay, what is the sum? We'll call it R for resultant vector. What's 0 plus 38.8 minus 14.8? 24.0 I. What is 22.0 plus 20.7 minus 31.0? The sum of these. $11.7 positive. So our resultant vector in rectangular form or in component form is 24I plus 11.7J. And what is that in polar form? Magnitude and direction. What is the magnitude of R? One step at a time. 24.0 squared plus 11.7 squared. Take the square root of. Get out your calculators. I'm doing number 9. Well, crud. Who asked for number 10? You did. No, I'm just plain doing the wrong one for you. But that's all right. We're going to, number 10 will be very quick. Let's finish this. 24 squared plus 11.7 squared, 712.89, take the square root, we end up with 26.7 whatevers. And the angle is the inverse tangent of 11.7 divided by 24.0. .0 degrees. Now, real quick, how do I know that this is the right number and that it's not 180 plus 26, which would be what, 206 degrees? How do I know that it's 26 degrees and not 206 degrees? Look at the vector in rectangular form. They're both positive. That means it's going this way and then it's going this way, which puts it right here, between 0 and 90 degrees. If it were going here, then it would be going negative and then negative, which would still give me a positive tangent, but it would be up to me to know that it's 180 degrees off. Okay? Now, number 10, given vectors A and B, what is A minus B? And what is B minus A? Okay? We've already done the bulk of the work because we've already converted them both into rectangular coordinates. So, what we want to find out is, first, B minus A, and then second, we want to find A minus B. And what we should see is that they are opposite of one another. So, B minus A equals minus 14.8 minus 38.8. Am I getting those numbers right? Yep. So it's the B component minus the A component. I plus the J, the 22 minus 20.7. J. What is this? Minus 14.8 minus 38.8. Minus 53.6i plus 22.0 minus 20.7, 1.3j. That's B minus A. Now, what is A minus B? It would be plus 38.8 minus negative 14.8, so minus a negative becomes plus 14.8 I plus 20.7 minus 22.0 J. Okay, what's 13.8, 14.8 plus 38.8? 20.7 minus 22. Now, look here. This is the whole point we wanted to see. The components are the same, but they're all opposite. So B minus A is the negative of A minus B. That was the whole point of number 10. Number 6. Do we have time to do number 6? Vector V1 is 6.6 units long and points along the negative x-axis. Vector V2 is 8.5 units long and points at plus 55 degrees to the positive x-axis. What are the x and y components of each vector? Hope everybody's got all this. Read the vector descriptions to me. What's the first vector? 6.6. Okay. And the second one is? Okay. 6.6 along the negative x-axis. What is that in polar form? Pointing this direction. What is that angle? 0 degrees, 90 degrees, 180 degrees, 270 degrees. So this is 6.6 at 180 degrees. What are we supposed to do with them? Yeah, convert them into rectangular and then add them together. Okay, well this one goes into rectangular coordinates very easily. First one, what's the rectangular form of that one? At 180 degrees, it's minus 6.6i. 6.6 times the cosine of 180. What's the cosine of 180? Negative 1. So it becomes 6.6i, and it has no vertical component. 6.6 times the sine of 180. What's the sine of 180? 0. Okay. Here we've got 8.5 times the cosine of 55 degrees I plus 8.5 times the sine of 55 degrees J. Somebody with a calculator. Plus what? 7.0? Okay. There it is in rectangular form. There's both of them in rectangular form. What's the sum? 6.6 plus 4.9? I plus 0 plus 7.0 J. So what's 6.6 plus 4.9? 11.5i plus 7.0j. That's a negative 6.6? It sure is, isn't it? So, what is that? Negative 1.7 I plus 7.0j. Does it ask for us to put that into Yeah. Put it into polar coordinates. What's the magnitude of this one? Magnitude of the resultant vector is minus 1.7 squared plus 7.0 squared to the 1/2 at an angle of the inverse tangent of 7.0 divided by minus 1.7. And here's where we've got to pay particular attention. First of all, what's this work out to? 1.7 squared plus 7 squared. Take the square root. Say again. 7.2 units. Now, 7 divided by negative 1.7. Negative 6. Okay, and you take the inverse tangent and get negative 76.35 degrees. That would be right around here somewhere. Minus 76 degrees. But you know from here that your vector goes left and then positive, which means it should be this at this angle. So what's negative 76 point whatever plus 180? .65, so 103, say 104 degrees to 3 digits. And there's your pole, that's the magnitude and direction. 7.2 at 104 degrees, not minus 76 degrees. Any questions? Your next class started a minute ago.